Hi y'all, welcome back for another round of physics, and we're just going to go at a couple more problems. Now I chose these problems because they are slightly more involved, of course, but also they're actually going to start bringing in some of these ideas about calculus, so I thought that this might be a good just place to start on that. So let's go ahead and pull up the question. Ding. The spring of a spring gun has a spring constant of K equals 500 newtons per meter and negligible mass. The spring is compressed, looks like 4.5 centimeters, with a ball of mass of 50 grams or 0.05 kilograms. It's placed in the horizontal barrel against the compressed spring. The spring is then released and the ball propelled out of the barrel of the gun. The barrel is, and again we see that it's the same size as the compression of the spring, so that the ball leaves the barrel at the same point that it loses contact with the spring. The gun is held so the barrel is horizontal. Okay, so we got an idea of what's going on here. We've got some sort of spring gun. So here's the barrel of a spring gun. Okay, and inside there, put here, there's some spring with a ball pressed up against it. Okay, and this distance, this distance is something like 4.5 centimeters. Okay. And of course, afterwards, if the spring's released, then it's exactly that distance. It's the distance of the barrel. Okay, there we go. So this 4.5 is the equilibrium distance, or I'll say either we'll call it the equilibrium or the natural length. Natural length. Okay, so we have an idea of what's going on here. Let's get to the first question. So the first question would be this. Calculate the speed with which the ball leaves the barrel, if you can ignore friction. Alrighty. Well, challenge accepted. Let's get at it. Well, I had the pictures drawn up, but let's go ahead. Let's get a system and a surroundings. Okay, for this, I'll call the spring and ball. And the surroundings, well, we could have things like the earth with the gravitational force. Gee, have some sort of barrel, maybe. Barrel. And we could call that the normal force. Okay. Yeah, that's fine. How about the initial state? Say just starts from rest. We'll put it that way. Starts from rest. So that instant that the ball is at rest, but the spring is released. The moment the spring is released, so that the potential energy of the system can be transferred into kinetic energy of the system. Final state, I'll say ball leaves gun. Okay. Well, we could do our same song and dance if we think about the earth and the barrel and think about the direction of the gravitational force and the normal force. We realize that these forces, I'll say, are perpendicular to the displacement. And therefore, the work done by these forces is zero. Okay. Now, of course, you see where we're going here. We'll say work is equal to the change in kinetic or energy of the system. We'll just put system. We've argued that the work is zero, so we'll put 0 over here, equals, in the forms of energy available to us in this problem, kinetic energy in the spring. Well, let's go ahead. Since we have energy is conserved, okay, we see that since work is 0, the energy of my system is conserved. So I'll write this down. Ke naught plus u naught. Okay. And we notice, okay, well, when the ball leaves the gun, the spring is at its equilibrium length, meaning how much potential energy does it store? 0. Get rid of this sucker. BC at natural length. How about the initial kinetic energy? Also 0. BC starts at rest. Okay. So we are left with, subbing in the definition of kinetic energy and spring potential energy, we have 1/2 mv final squared equals 1/2 k, I'll put x naught squared. All of the energy stored in the spring goes into the kinetic energy of the ball at the end. Oh, goody goody. Can cancel out the 1/2s. 1/2s go away. And we end up with an expression that says our final speed is equal to the spring constant divided by the mass square rooted times how far the spring was stretched in the first place. Okay? Good. Sub in our numbers. So 500 for K, we have that up here. 0.05 for the mass right here. And the initial compressed length. Okay. And we get something that says, I guess I'll do that over here. Run out of space, excuse me. So V final is equal to 500 divided by 0.05 square rooted times 0.045. And you do all of that, you end up with, hey, this ends up being 4.5 meters per second. There's our final speed. All right. Good. Well, let's go on to the second part then. Oh, we'll go ahead and let's go ahead and clear the table here. Okay. And you'll see that I've got the second part of the question up now. Calculate the speed of the ball as it leaves the barrel if a constant resisting force of 7.5 newtons acts on the ball as it moves along the length of the barrel. Whoa. Okay, well, perhaps I got a little overzealous with my deletions. So here, let's do this instead. So let's get rid of this. We'll get rid of this. But here, I'm gonna keep these pieces. Okay, right there. Keep that from the last time. Except now we have a situation where we argued right here originally that these two forces don't do any work on the system. But now we've been given a third force that we should also include, probably associated with the barrel, and we'll call it the frictional force. So we'll assume, or a resistance force, but we'll assume that that also is due to the barrel. So again, we can argue that the gravitational force and the normal force do no work on my system. But this resistive force absolutely does, one that I've called the frictional force. So where does our approach change? Well, we still need to write down the work is equal to the change in energy of the system. That hasn't changed. But now, right here, instead of setting work equal to 0, we're going to have to set it equal to the value of the resistive force dotted in to my displacement. Over on the right-hand side, we still can write the kinetic energy. We can still write the change in potential energy of the spring. Okay. Now, by nature, we said, hey, this is a resisting force. So what does that mean about the direction of this force with respect to the displacement of the ball? They're in opposite directions. Okay. And if they're going in opposite directions, what can you tell me about the sign associated with this? It's negative. Good. Okay, so I'll put a negative sign in here, and these are presumably in the same direction. And so we'll drop our vector signs. We'll call this the frictional force. We'll call this the displacement, delta x. Of course, over here, our same song and dance applies about the final potential energy and the initial kinetic energy. So I can put kinetic energy final minus the initial potential energy. Now we're home free. We'll move this to the other side. So we get kinetic energy final equals the potential energy. This is what we had from the first part. But then we have this leftover minus F of the resistive force times our displacement. Let's sub in our definitions. 1/2 mv squared equals 1/2 kx naught squared minus this sucker. And now you can see that that interaction is pulling energy away. In other words, it no longer does 100% of the potential energy go into the kinetic energy. No longer is that the case. Instead, some of it gets bled off by this frictional force, the work that the surroundings does on the system. So we should expect a value lower than 4.5 meters per second squared. We'll go ahead. I'll do one more. Of course, your algebraic steps will get you there. We get something like kx naught squared minus, put 2 here, f of r delta x. That whole rigmarole divided by m and square rooted. So there's now my expression. Keep in mind, delta x is, again, the length that the ball travels in the barrel. Okay. Oh, subbing in numbers. Let's go ahead and take a gander here. Of course, we're given the value of the frictional force. So we are off and rolling. We have final equals, we still have our 500. We're told that it's 0.45 centimeters squared minus 2 times, well, my retarding force is 7.5 newtons. That's given in the problem. And our delta x, again, is that 4.5 centimeters. Our mass, 0.05, and we square root the sucker. Now, unless I botch something, which is perfectly possible, I got something like 2.6 meters per second. So instead of the 4.5, we're now down to about 2.6 meters per second because of this retarding force as the ball travels down the barrel. Okay. Let's go ahead. I'll pause and get the next question up. Well, we've got the new problem up now, the next part. For the situation in the previous part, at what position along the barrel does the ball have the greatest speed? What is that speed? So first of all, I'm going to keep the system and the surroundings the same, and the initial starts from rest. But the final state, you've noticed, I've already erased it. The final state, we want the ball at max speed. Okay. And maybe instead of saying greatest speed or max speed, maybe I say extreme. And hopefully that pings something in your head about calculus. To be continued. Well, let's go ahead. We'll set up our usual. Our work is equal to the change in energy of the system. And again, we have our retarding force times our displacement. And this will be equal to, I'll put our kinetic energy final minus our kinetic energy initial, plus our potential energy final, not gravity, but spring, minus our initial potential energy. And keeping in mind what we have as our initial state, we can still say that the kinetic energy is 0, the initial kinetic energy. But remember, we changed our final state. The ball's at V max. That means that we can't necessarily set our final potential energy to be 0 anymore. Okay. Now, if I'm thinking about it, let's say, let me draw a little diagram, because sadly I've screwed this up once tonight. I got halfway through the problem and I realized I did it wrong. So let's do this. Here's the spring gun again, and keep in mind this barrel is a length d, and I will call the distance that the ball has traveled x. And so the distance that the spring is away from equilibrium is d minus x. Okay? Let's go ahead and substitute in the rest of our definitions. We have negative f, and our displacement per my diagram is x. This equals 1/2 mv squared plus 1/2 k d minus x squared minus my initial potential energy, 1/2 k d squared. Rock and roll. Let's get v squared by itself. So I multiply everything through by 2, so I'll make this a 2. And we can get rid of these. And I'm going to move these two terms to the other side, so I get something that says mv final squared equals negative 2fx minus k d minus x squared plus kd squared. So say minus, move this over, I get a minus, move this over, I get a plus. Okay, good. And of course, the last thing to do is to divide by m. Rock and roll. Now we're at the position where we need to use our calculus. We're going to take a derivative and we'll set the derivative equal to 0. Okay. Now, rather than doing a square root and a product rule or a chain rule or whatever, I guess it would be a chain rule, I'll just do the implicit differentiation, I believe is what it's called. So taking the derivative of this side, I get something that says 2v dv dx. And on the right-hand side, first term, I get negative 2f. The second term, I have negative k. And since my x is in a parentheses, I power rule it, so the 2 comes down. I multiply by d minus k, whatever's inside the parentheses, and it's to the first power. 2 minus 1 gives me the first power. Then I got to chain rule it. I have to take the derivative of everything inside the parentheses, negative 1. Of course, this third term, you notice it's a constant and a constant, so the derivative of that is just 0, unchanging. Yeah. Oh, goody goody. Look at this. Everything has a 2, so I'll get rid of those guys while I'm at it. Now comes the point of, hey, wait a minute, to find the extreme value, what I need to do is take the derivative and set it equal to 0. So that's what we're going to do. And I get 0 equals, moving the m to the other side, so v times 0 is 0, m times 0 is still 0. So I end up with negative f plus k d minus x. Bit of algebra, f over k equals d minus x, or x is equal to d minus f over k. Boom, got it. Awesome. So if we substitute in our values here, doth my calculator mistake it, I have something like 0.03 meters. In other words, it hits its max speed at 2/3 the distance down the barrel. So we'll put that there. Cool. Well, let us see if we can actually figure out what that speed is. And because I like doing it so much, I think I'll work in terms of variables first. So we actually have the speed that we want right here. This is really what we want, is right there. So let's kick that out. We'll move that to right here so that we have it saved. And let me get rid of the rest of this rigmarole. Okay. Well, let's go at it. I'm going to take this expression. I'm going to plug it in there. So I get something that says equals 2f negative. We have d minus f over k minus k d minus f over k squared plus kd squared all over m. And this is a k. That was ugly. And that's v final squared. Well, if we go through, let's take a look-see here. Well, I have d minus f over k, so that would give me k times f over k squared, right? This d cancels that d. I have plus kd squared. And over here I have minus, I'll distribute it out, fd minus minus, so I have a plus 2f squared over k. This would be a minus still. That whole rigmarole is, of course, over m. Of course, we see now this and this are the same. So this cancels out one of those. Just checking my notes. And so we have equals. Well, let's see here. We have something that says, well, okay, we'll do it like this. Let me move the, let's put a k in here everywhere. So I'll multiply top and bottom by k just to get rid of the compound fractions. And I get something that says kd squared, that's this term, okay, minus 2fkd, that would be this term, plus f squared, that whole rigmarole divided by km. That will be equal to v squared. Okay. Well, let's go ahead. Of course, you have all of these numbers. This is 500 times 0.045. That whole quantity squared, minus 2 times 7.5 times 500 times 0.45, excuse me, I really want to put an extra 10 in there. 0.045 plus 7.5 squared. That whole thing divided by 500 times 0.05. And unless I did something goofy, after I plugged this all into my calculator, I got a value of 9. Yeah, v squared is equal to 9, or that v is equal to 3 meters per second. So at 3 centimeters down the barrel, it's moving at 3 meters per second. And of course, if you look, the speed at the end of the barrel, I believe we had something like, I'm looking right now, I had something like 2.59. Is that right? We'll have to look it up. Boom. And we're done. Cool beans. So that's just another example for you. Just thought that I would throw that on. Hey, thanks for your attention. I'll see you next time.